Well, good evening. My name is Joel Quijano. I'm going to talk to you about dynamic tensile properties of sandstone subjected to wetting and drying cycles. So, as an introduction, due to the long-term exposure to the hydrosphere and atmosphere, rock materials are always suffering various kinds of weathering. The rock deterioration to different degrees after cycle wetting and drying treatments was assisted by change in physical properties such as a bulk density, weight loss, water absorption, effective porosity, and P-wave velocity. The objectives of this research are to understand the deterioration in rocks induced by cycling wetting and drying treatments and its effect on the dynamic tensile strength of rocks. In this study, the microscopic features of sandstone specimens were observed using the scanning electron microscope technique, which is called SEM. Well, talking about the experimental material and methodology, in this study, the rock material is a fine-grained homogeneous sandstone widely available in the northwest of Kunming. That's a province of China. The mineralogical composition for the sandstone was determined by energy dispersive X-ray spectrometer. The sandstone is mainly composed of quartz, 42 and 25%, amphasite, 16 and 85%, calcite, 13 and 9%, hematite, 11 and 19, and feldspar, 9 and 0.08%. Some other minerals composition like mica, it was like 0.8%. So in this graphic right here, we can observe what we just explained about the experimental material. So what was the testing methods? And there have been two types of testing methods for precisely measuring to the dynamic tensile strength: direct and indirect tension test. For dynamic direction tension, previous research have developed several different versions of dynamic direction tension technique based on the principle of split Hopkinson bar, also called split Hopkinson tension bar. And how was the specimen preparation? All the specimens used in the dynamic Brazilian disc tests were manufactured in accordance with the standards of ISRM suggested specification to ensure high uniformity and repeatability of specimens. All specimens were prepared from a single sandstone block. The sandstone block was firstly drilled into cylindrical cores with a nominal diameter of 5 mm using a diamond coring device, and then the cylindrical cores were cut into BD specimen with an average thickness of 25 mm. After that, the ends of the specimen were polished using a phase grinder to make the surface roughness less than 0.025 mm and the end surface perpendicular to its axis less than 0.25. Here we have the two experiments that we already talked about it. At the left, we have the variation of water content with C of sandstone in a single wetting and drying cycles in both of them, but at the left we have the liner, and on the right we have the semi-log coordinates. The conclusion of the experimental were that the wetting drying cycles have remarkable influence of cycle properties of sandstone. The test results show that with the increase of cycle number, the density, P-wave velocity, and SDI of rock specimen decrease, while the water absorption and porosity increase. Another conclusion is that the internal microcracks, growth, and grain deterioration can be found in the same images of sandstone after different wetting drying cycles. Fractal analysis further indicates that the success cycling wetting drying treatments increase the density, complexity, and interconnectivity of the microcracks. Thank you.